Okay, this is the first PowerPoint outline you're going to see me do. It's going to be on Chapter 2. This is the first chapter in the first unit of the online Earth Science course. I chose these 5 chapters, chapters 2 through 6, for the first unit because it essentially walks students through the Earth's rock cycle. So it talks about, in this chapter specifically, what rocks are made out of and what composes that matter. Future chapters are going to talk about different processes to change rock from one type to another, and then the last 2 chapters will be about how does weathering happen and how are rocks degraded back into the rock cycle to form newer rocks. All right. Just a note about these PowerPoints. These PowerPoints are given to the instructor as a part of the instructor resources for the course. What I did is I edited them such that only the sections that we're covering for this particular chapter are going to be outlined in these PowerPoints. And again, as I talked about during the syllabus, not all of the content for Chapter 2 that you're responsible for will be found within this PowerPoint. All right, so the first thing, we want to talk about the definition of a mineral. So there's 5 qualities. So it has to be natural, which means it can't be created inside of a lab. So if you think of something that's lab created, you could have lab created gemstones, something like a cubic zirconia. That's not naturally occurring. That's created in a lab. So those would not be considered a mineral because it's not naturally occurring. It has to be inorganic, which means it can't have the element carbon within its structure. It has to be solid, so it cannot be a liquid or a gas. And it has to possess an orderly internal structure of atoms and have a definite chemical composition. So what that last one means is it has to have some type of chemical formula. So for example, water, which would not be a mineral, but it has a chemical composition that's H2O, and that is definite. It's not changing for that substance. So for a mineral, something to be a mineral, it has to have that definite composition. So a rock is simply defined as any piece of matter that is made up of minerals or mineral-like matter. Now, what we'll do is before we go into what makes looking at different types of minerals, what we're going to focus on is how could you make matter to begin with? What's its lowest composition that we're going to be worrying about in this course? So the lowest piece of matter we're going to talk about are the constituents of what are called atoms. You probably have seen this before, seen diagrams like what you see here on the right. So this hopefully is just a review. There are particles that are smaller than the proton, neutron, and electrons. You may have heard of quarks before or some other smaller, what we call in physics, elementary particles. We're not concerned with those. We only want you to be aware of these 3 small particles that make up atoms. So first we have a proton, which is the positive charge inside of an atom. We have electrons, they're the negative charges, and then neutrons have no charge. Now you might be surprised, but charge ends up actually being a physical property of a material. So you can take, let's say, an element that's composed of the same type of atoms, and you can change its charge, but it doesn't actually change what that substance is. So we say charge is a physical property. Now, you may have seen this classic picture of electrons orbiting the nucleus of an atom, kind of like how the planets in our solar system orbit the sun. That's what we call the classical model to the atom. What we've found out, and it's probably been a little bit less than 100 years, but in the beginning of the 20th century, and I think it was 1910s, a new type of a model, which is a quantum mechanical model for the atom, was developed. So instead of an electron orbiting the nucleus of an atom like a planet, it turns out there's possible orbitals or places around that nucleus where the electron could exist. And there's a probability to find that electron at a specific location. So it's a more complicated model for the atom, and it turns out that this model down here where you see marked as B with this electron crowd, that seems to be how the electrons work when they're orbiting that stationary nucleus. All right, so I'm going to show you in a moment something called the periodic table of elements. It lists a bunch of different information about all of the possible elements that exist. Now, many of these elements on this table you're about to see are naturally occurring, but some of them are not natural, so we would not be able to classify them as minerals. Okay, so they're defined by their atomic number. So the elements in the periodic table, you're going to see the atomic number listed for different elements. And just as an example, carbon has the atomic number 6. This tells you how many protons are in the atom's nucleus. So by determining the amount of protons in the nucleus, that will tell you what the element is. You might be wondering, well, what happens when you change the amount of electrons in an atom? Well, that's when you change the charge on that atom. So for example, if you have carbon and it has 6 protons, a neutral carbon atom will have 6 electrons. So that means you have 6 positive charges canceling out with 6 negative charges. That atom becomes neutral. As you start transferring electrons in and out of the atom, that's how you change its charge. So we call a positively or negatively charged atom an ion, and it simply means that you're gaining or losing electrons, but it does not change your chemical state. If you have a carbon atom with 8 electrons, it's still carbon, but it's just negatively charged because you have more electrons than you do protons. All right, so here's that periodic table. You'll see here, I'll just point out carbon because I use it as an example. The number 6 is above the symbol for carbon, which is a capital letter C. So 6 signifies the carbon number. The number below the symbol C, 12, this is actually what's called the mass number or atomic weight of that specific element. This tells you the total weight of the nucleus with a little bit extra for the electrons in that specific element. All right, so how do you tell the number of neutrons in an atom? You simply take the atomic weight, so in this case 12, and subtract the number of protons. That's going to give you the number of neutrons in the element. The last thing I'm going to mention about the periodic table is that the columns that you see are special in that each column represents elements that have a different number of electrons in its outermost energy cell. So the outermost shell in an atom is called the valence shell, and something called the octet rule dictates how many electrons want to be in that outermost shell. So atoms gain, lose, or share electrons until their valence shell has a total of 8 electrons. This is important because when you're going to bond 2 elements together to make something called a molecule, when the bonding occurs, the most stable atoms like to have that shell completely full. The next amount of stability would be 1 electron in the shell or having 7. All right, so it wants to try to get a total of 8, and then the farther away you get to 8, the more unstable the molecule or the element. So I'm just going to go through different ways to bond elements together. The first type is called an ionic bond. This is when you take 2 atoms and you put them together, and an electron is transferred from one to the other. So when you transfer out an electron, that means you're going to have a net positive charge because you're losing some of your negative charge. When you gain an electron, that's going to give you a net negative charge, so you end up becoming negative in totality. So what you have in this example with table salt, sodium chloride, NaCl, when the sodium atom gives up an electron, it becomes positive, and when the chlorine atom gets that extra electron, it becomes negative. And this turns out to be a stable state to make up the molecule sodium chloride. So when you have atoms giving up electrons to make ions and then coming together, that's called an ionic bond. Another type of bond is called a covalent bond. This is when 2 elements end up sharing 1 electron. So it's not that an electron is given up, because that electron can still be found outside of either of the 2 nuclei in the combination. So in this example, you have 1 hydrogen atom, so the cloud of electrons is represented by this blue sphere, and then you have the second one, and then when you combine them, you get just a different shaped electron cloud, which means that any of the 2 electrons that can be found in this molecule could be found orbiting either of the nuclei. So when you're sharing an electron between atoms, that's when you have a covalent bond. And the last type we'll talk about, because many of the materials you're going to see in this course are metals, we have something called a metallic bond. So you can pack a lot of metals, which tend to be the elements in the center of the periodic table. You can pack those together, and when you do so, the electrons in these elements tend to move freely about all these different nuclei. So it's sort of like they're sharing the electrons. Now, these electrons that are shared, they end up making what's called this, quote, sea of electrons. So as an example, let's say you take copper and you wanted to make a conductor out of it. You wanted to connect an outlet in your house to the main electrical box, let's say in your basement. Copper is a good conductor because it has a large sea of electrons that can be pushed through the wire to form an electric current. So this idea of a metallic bond is important because a lot of the materials that you may deal with in your everyday life are actually metals. All right, so just to end the chapter, we're going to look at some physical properties of minerals. These are basically just definitional, so I'm not going to go through them too much. We have habit, so this is the shape of the crystal that makes up the element. You have luster, so this is what light does when you shine it on the mineral. So is it reflected? Is it absorbed? You have color, that's pretty obvious. Streak would be when you take the element and rub it up against something. It's going to leave powdered form of that mineral, and the color of that powdered form is important. It seems to be consistent across different mineral types. Then you have hardness. This is the resistance to scratching or abrasing something, and then cleavage is how it breaks. And there's just some pictures here showing you this. So here's an example of luster. So you can see the one on the left here. All right, this is a material that doesn't reflect light, so a lot of it's absorbed, and black tends to be the color that you see when most of the light is absorbed. And then you're going to see on the right, when white light is shown on this piece of material called galena, a lot of it's reflected. So this element, or this mineral on the right has a different luster than the one on the left. Color is actually not used that often, only because, as an example, if you look at all the different types of fluorite on the left-hand side, 3 of them have a purple color to them. And it would be very hard. This one might be a dark purple on the left, but then these 2 would be very hard to describe the difference between the 2. And when you want to describe the difference between something, you want to do it scientifically. So you wouldn't want to say, well, this is a lighter purple and the one on the right is more University of Scranton purple. You wouldn't want to say that. You would want to be scientific about the differences. But it can be used to at least tell some major differences between minerals. So here's streak, like I mentioned. So if you take a mineral like this and then rub it up against something so you have some powdered form of that mineral, the color of that powdered form doesn't necessarily always match the color of the actual mineral, which is interesting. Then you have crystal shapes, so these are all kinds of crazy different shapes. I'm not going to get into it. Just know that's what habit means. And then hardness, there's a scale to this where diamond is the most relative hard substance that we know of, and then it decreases as you go down here. Cleavages would be how the minerals actually break when you try to break them apart. And there are also some other physical properties. You have fracture, which is the pattern of breakage when you would go to break something. Specific gravity, this is just the density of the mineral. And then tenacity, that's a pretty cool word. It's just the resistance to cutting, breaking, bending, or deforming. This is an example of a conchoidal fracture. And there are some other properties which aren't typically used to identify minerals, like taste. That's kind of weird, but I know of scientists who taste some things, and if it's salty, you can kind of identify that there might be a chloride atom involved if it's a salty taste. Smell. Things that have sulfur in it tend to smell like rotten eggs, so you could identify if something has sulfur in it. Elasticity, malleability. Double refraction has to do with when light passes through the material, so that's a little different than reflection. Magnetism, so the susceptibility of the material to a magnetic field. How it feels, is it soft, is it brittle, is it hard, is it sharp? And then reaction with different types of chemicals, and the example they give you is hydrochloric acid. All right, the end of chapter 2 talks about different mineral groups. And I didn't want to cover that, but I do want to mention a few things about minerals that are commonly found in the Earth's crust. So this is the outermost layer of Earth. Now, there's actually only a few dozen rock-forming minerals, believe it or not. And the most abundant atoms, so the most abundant elements in the Earth crust, if you would believe it, it's oxygen, and this is again by weight, and by silicon. All right? And then here are some of the other elements that you would find in the Earth's crust that are rock-forming materials. You have oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium. And here's a nice little pie chart just showing you the relative percentages by weight that occur in the crust. So you can see, again, oxygen is prevalently there. Now, silicon is important because if you've ever heard of an electronic device called a semiconductor, so this is actually an electronic switch. It allows you to change the direction of current in circuits. Silicon is one of the main components of semiconductors. So because it's so abundant, it could be easily mined and used to make these devices. So if you're watching this on a computer, there are semiconductors in your computer working right now to power your device and to transfer information from place to place inside your computer. Your cell phone has semiconductors. So the fact that silicon is so abundant on the Earth's crust, easily accessible, that's an important thing. Just the reason we have all our technology that we have. And then another couple important ones are iron and aluminum, because we do a lot of building with those two materials. All right, so that's the end of my introduction to Chapter 2. Some of the other chapters will be a little more interesting. I'll have some demonstrations, so some videos involving those. But this one was just a good first day chapter outline for you to do. So just some information that you have to absorb. So, all right, good luck, and I'll see you next time for the next PowerPoint outline.